In the last couple of videos, I gave you an admittedly unsatisfying conceptual definition of what entropy is, but hopefully that example helped you see how you can apply the entropy balance in order to solve problems. That's really the important part of what I want you to get out of this class is applying the things that you know in order to solve problems. I think that's the number one reason I think why thermodynamic classes are a little confusing, because you can't automatically always apply the knowledge that you're learning in order to apply a problem. So with that, I'm going to conclude the review of entropy. So that was chapter 4 in the Sandler textbook. Now we're going to move on to chapter 6, which covers equations of state, partial derivatives, evaluating thermodynamic properties, and all that good stuff. And the first question I want to tackle is the question of what do you do if thermodynamic data is not available? So I'm going to take us back to that example of the Joule-Thomson valve. So in a pipe with gas flowing, we've got a valve here. Recall that in this problem, we knew what the flow rate was. So we know M1 or equivalently N1. We know P1 and we know T1. So these are all known properties. And then at the outlet, because inflow has to equal outflow, we know M2 or N2. And we know P2, but we don't know what T2 is. And just to remind you, we set up the energy balance, and the energy balance told us that the specific enthalpy at state 2 was equal to the specific enthalpy of state 1. Or I should say stream 2 is equal to that of stream 1. And then before, what I did was I said, well, if we know what H as a function of T and P is, then we can just go ahead and calculate what the enthalpy is, because we know what pressure and temperature are for the inlet stream. And for the outlet stream, we know what pressure is and we know what H hat has to be, so therefore we can calculate T. What I breezed over is what is this function that relates H to T and P. The way I solved this problem before, and this is always what you should try to do first. So the first step, or the first thing you should always try, is to see if you have data. See if data is available. And if it's a common chemical that you're working with, so I said steam was the first one that we did. And steam, obviously, you have steam tables in the back of the book. That's probably the most common chemical that's used for these thermodynamic problems. So definitely water's been studied. But a lot of other common chemicals have been studied as well. So I'm going to clip the diagram for ammonia. So if you look in an external resource like Perry's Handbook, or if you go online to the Engineering Toolbox or NIST, you may see a diagram like this, a pressure enthalpy table. So this one is for ammonia, and admittedly it's very confusing, but the idea is if you know any two of the coordinates that are on this diagram, so just from looking at it, we definitely have pressure on the y-axis and enthalpy on the x-axis. We've also got temperature lines on here. It looks like we've got entropy lines on here and some other ones. Sometimes it's not as easy to read as you would hope, but oftentimes the footnotes of the table can help you in reading it. This particular footnote doesn't seem to be too helpful. But there's a trade-off to using these. So oftentimes the accuracy of the table itself is going to be very good, but you're going to be limited in terms of how closely you can resolve the lines. In other words, if you don't read the table accurately, your data is not going to be that accurate. So you're limited in terms of how you can make out the resolution of the lines. But still, I think this beats an equation of state, just because you assume that you would be able to read this diagram if you were careful enough, or if you were motivated enough. So you assume that the data itself is good, and maybe you just need more practice in reading these diagrams. I find these diagrams very difficult to read too, by the way, so you're not alone in getting a headache trying to figure out what all these lines are. But in the absence of data like that, say you have a not so common chemical, your backup plan is going to be figuring out or modeling the equation of state. So you need a model or equation of state. So a model is just an equation that closely approximates all of these lines. So in theory, there would be an equation for each one of these lines, or for all the lines together that incorporate whatever variable that you're trying to relate, that you could redraw these lines on the graph if you wanted to. All right, so just as a fair warning, we're going to get into a little bit of confusing calculus. And for now, I'm going to present a couple of rules of calculus. And in most cases, I'll either refer you back to your Calc 3 textbook or your multivariable calculus textbook. I'm not sure if it's called Calc 3 here. But try to take these derivatives and these math properties just as face value. Again, try not to get caught too much in the details. The number one question that I want to guide you anytime you're doing a problem like this is, how can I relate what I know? How can I relate what I know to what I don't know, or to what I seek to know? To what I seek to know. All right, oftentimes when I'm doing steps like this, you may have the question of, well, how did you know that you had to do this particular step in this particular instance? And truthfully, you wouldn't necessarily know that. So if you're trying to do a derivation like the one I'm about to show, there's multiple ways that you could arrive at the final answer. And oftentimes when you see like the final version worked out, it's just because it's been streamlined after seeing what works and seeing what the most direct way to get there is. So just an introduction, we'll do some more of these as we go. The first rule of differential calculus that you have to accept as face value is the partial derivative property. So this says that for any property x that is a function of other properties y and z, so we're going to say that x is equal to x as a function of y and z. And the idea here is that x, y, and z are just placeholders for any thermodynamic properties. So I'll plug those in later. The partial derivative, again, says the change in x, so that is dx, is equal to the partial of x with respect to y. So that's partial. So my partials, I kind of draw like a Disney D, or like a backwards 6. And my total derivatives are like a Roman alphabet D. So this is total, this is partial. So partial x with respect to y, and then in thermo notation, what we do is we put parentheses with the variable that's being held constant outside. So it's very important to keep track of the variables that you're keeping constant, because these are anything outside the parentheses you have to write, because it's not apparent that x is also a function of z. So this tells you that x is a function of y and z, but z is being held constant in this case. We say that x is not a function of anything else. X is not a function of k, for example, times the total change in y, plus the partial of x with respect to z at constant y, so same notation, dz. So just as a useful mnemonic, what I like to remember is like the partial y and the dy kind of cancel out. That's not proper mathematics, so don't think of it like that. That just helps me to remember how this particular rule works. And then also another part of the mnemonic is I have to take the partial with respect to each variable while holding the other one constant. I think this is referred to as the chain rule in calculus. Don't quote me on that one. All right, so as I said, you can use this rule to relate any thermodynamic properties. So say that you said that H was S, and Y and Z were, let's say, H. And these, anytime that you're using an extensive property, you want to make it intensive as well. So it's all these are underbars, so H and T. So I can just plug in, anytime I see an X in this equation, I'd plug in S. Anytime I see a Y, I plug in a H underbar. Anytime I see a Z, I plug in a T. All right, so how does this help us back in the Joule-Thomson example? Well, again, I want to relate what I know to what I seek to know. So in this case, what I seek to know is dt. Sorry, my tablet is glitching a little bit. I seek to know what dt is because I want to figure out what t2 is. All right, so I want to go from t1 to t2. What do I know? Well, I know dp. I know the change in pressure. I know what P1 and P2 are, so therefore I know what the change in P is. And I also know what the change in dH is. So I wrote dH underbar here, and I wrote H hat before. Those two things are not necessarily equivalent. Remember, H hats are specific properties, so that's enthalpy per kilogram, whereas H underbar is enthalpy per mole. Most times in thermo, we write in a molar basis, so most of the times it'll be H underbar. But if you know what H hat is, you can convert to H underbar just by knowing what the molecular weight is and converting to grams from kilograms to moles that way. All right, so I'm going to relate what I know, P and H underbar. I shouldn't have done that because now it looks like T underbar. T and P don't need underbars. Relate what I know to what I seek to know. Okay, so I'm going to say that T is X, H is Y, and P is Z. All right, so I'm just going to apply that equation for this situation. I'm going to erase this one. That one was just as a demonstration that I can do it with any variables. So hopefully I explained why I'm choosing these three particular variables. And in another situation, you may choose three other variables to stand in for X, Y, and Z. Okay, so T is a function of what I say, it's H and P. So I need partial of T with respect to H at constant P times total dH and plus dt dP at constant H bar dP. Okay, how does this help? Well, I said that H is constant, right? So I know that dH underbar is 0. So therefore, if this term is 0, this whole term goes away as 0. And now I'm left with this dt dP at constant H dP. How does that help? We kind of appear stuck here because I said that you need to know what the function T is as a function of P and H. And if you did know that, say you knew, for example, that T was equal to 3P plus H. It's not equal to this, by the way. I'm just illustrating. This is a simple equation that could possibly work. All right, you could just take the derivative of T with respect to P. So partial T with respect to P is simply just 3 in this case, and then you'd plug 3 in, and then you'd have an equation, right? But we don't know what this function is. That's the problem. Do not, by the way, this is another pitfall that you could fall into. Do not say, you may be tempted to say that we know what the ideal gas law is. So let's assume that it's ideal gas. So we could say that PV bar is equal to RT. If we wrote this in terms of T, so we can solve for T and say it's PV underbar over R, and then don't say that the partial of T with respect to P is V over R. You cannot do that, and that is because, what did I say, V underbar over R. You can't do that because if this were, instead of H underbar, if it were dt dP at constant V underbar, that would be okay. You could use this ideal gas law in that equation because it tells you that T is a function of P and V underbar, which is what the ideal gas law is. However, partial T with respect to P at constant H tells you that V underbar can't be in this equation that we use, right? It has to be an H underbar instead, and we don't yet know what that is. So again, it appears like we are stuck. But again, think back to the guiding principle of this section of how do I relate what I seek to know to what I already know. So how can I relate partial T with respect to P at constant H to something that I already know? And this is where we're going to do some more calculus properties. All right, so another calculus property that I want to introduce now is the triple product rule. Or maybe review now, maybe you know this already. The triple product rule. And I'm going to use the same notation where I say X, Y, and Z. So triple product rule says partial X with respect to Y at constant Z times the partial of Y with respect to Z at constant X times partial Z at constant X. I'm sorry, partial Z with respect to X at constant Y is equal to -1. So my mnemonic for this one is I start with X, Y, Z, and then I multiply through, and every time I just cycle the variables clockwise. You could also cycle counterclockwise. That'll work out the same. It might not appear like it, but remember that x, y, and z can stand for anything. So you could simply just reverse what you are calling your variables. All right, so I'm not going to get into the derivation of the triple product rule. You can, again, go back to calculus or look it up on the internet if you're interested in how this property comes to be. But here I'm just going to simply use it in order to illustrate what I want to illustrate. And in general, I'm not going to get into like why calculus properties are the way they are. We're just going to, I'll present them and then we'll use them. So again, I'm going to refer back to saying x is t, y is p, z is h. I'm not sure if that's the same convention we had before, but again, it should work out either the same way no matter what your variables are. All right, so I'm going to say, my light blue is going to be my equation pen, by the way. So what I like to write my math terms in, dt dp at constant h times dp dh at constant t times dh dt at constant p is equal to -1. Okay, how does that help? Well, we've got the term that we had in that equation, dh dp at constant h, and now we can relate it to these other two. So if we take the other two over to the other side, we're left with dt dp at constant h is equal to -1 over dp dh constant t dh dt at constant p. Okay, it looks like we're still kind of stuck because we don't know what p as a function of h and t are, or what h is a function of t and p are. Remember, that's what we wanted to figure out in the first place. I'm sorry, not what we wanted to figure out in the first place. We wanted h as a function, or we wanted t as a function of h and p. But anyway, this is another useful property that you may remember from Thermo 1. Remember, there's a definition that you can apply. You can say that the heat capacity at constant pressure literally is dH dt at constant P. So this is just something that you take as a definition, so heat capacities. We introduced this in MEB too, by the way, so that might look familiar. So here I've got a dH dt at constant P. I'm going to replace that with the heat capacity. And now it looks like we're getting somewhere. So remember, the goal here is to relate what I want to know. I want to know dt dp at constant h to what I do know. So Cp is hopefully something that I could look up. Even if I don't have detailed thermodynamic data, I may be able to find what the heat capacity at constant pressure is. But we still have this pesky dp dh at constant t term, so what do we do with that? It's time for another calculus identity. So I can say that 1 over dx dy at constant z is equal to, I don't know what this is called. Maybe it's the reciprocal rule or something like that. I can just flip it. So I can say that is equal to dy dx at constant z. All right, so I'm going to employ that now in applying it to this equation. So I got dt dp at constant h is equal to minus 1 over Cp times dH dP at constant T. And that step looked like it didn't really help us all too much because I still don't know what H under bar as a function of P and T is. All right, so time for another calculus property. This one is the expansion rule. Expansion rule. And this one goes, for a partial of this form, dx dy at constant z, I can define two more properties and put them into these partials. So this is going to look like it complexifies things, but everything should cancel. Or I'm going to use it, it's going to look more complex, but it'll cancel later. So I'm going to define a k variable and an L variable. So I'm going to say partial of x with respect to k at constant L times partial of k with respect to y at constant z. So again, the way to remember this is like the partial k's cancel out with cancel in air quotes, because that's not necessarily how calculus works, but it helps my brain to remember how these rules go. Plus dx dl at constant k times dl dy at constant z. So the two new variables k and l get flip-flopped in the two terms. All right, so how does this help me now? So now I've went from wanting to figure out what dt dp at constant h is to wanting to figure out what dh dp at constant t is. So I need to define two more variables. So I'm going to say that k is equal to p. So I can double that up, by the way. I don't have to have unique variables. This all works if I assign the same variable twice. So p is equal to k and y, I think it is, or z, one of those from above. And L is going to be equal to S underbar. All right, so I want to find what dH dP is. dH dP, and it's cumbersome to say dH underbar every time, so anytime I'm saying H or S, assume it's always underbar, unless I say otherwise. Okay, dH dP at constant T, T. That's what we want to find out. That's what we're on, figuring out what it is. So I'm just going to use this expansion rule and say dH, K is P, remember, dH dP at constant S times dP dP at constant T. And that's not a typo, dP dP. So the change in P with a corresponding change in P will always be 1. So you could think of it as if I change a variable by a certain amount, that same variable will have changed by that amount every time. So if I change P by 5, my change in P is also going to be 5. Plus dH ds at constant P times ds dP at constant T. All right, as I said, it looks like I've made things way more complicated because now I have entropy into the equation. I've got S underbars here now too. How does that help? Well, now I'm going to do a lot of hand waving, and don't worry because we'll come back to this next week in terms of how I can use these relations. But I have 3 relations that I want to use. I'm going to say that dH dP at constant S is equal to V underbar. So again, don't worry about how I got this. I'll go through the derivations for this next time. I want to get to the final part of how we relate what we want to know to what we already know. All right, dH ds at constant P is equal to T, and then by a Maxwell relation, ds dP at constant T is equal to negative dV dt, dt at constant P. All right, so 3 steps that I'm skipping a lot. As I said, we'll go back to it, but I want to plug all these terms in to my equation above. So dH dP at constant T is equal to dH dP at constant S is V bar plus dH ds at constant P is T, and ds dP at constant T is minus dV underbar dt at constant P. There's my dt. Okay, that was a lot of math. I want to kind of bring it back, and we're concluding now. We're almost to the point of where we know what everything is. I want to take a step back and look at this equation, V plus T times dV dt at constant P. You might think that that doesn't look any better than before, but again, I want to bring it back to the fact that T and P are measurable properties. We have a thermocouple or a thermometer for T, we have a pressure gauge for P, and to a lesser extent, we can even measure V bar. These 3 properties are readily measurable. All right, in contrast, H, S, U, those are not readily measurable, so those are less helpful. And remember, for an unknown chemical, it's very, very rare that we would have those. All right, so I'm going to take the entire expression for dH dP at constant T and plug it back in there, and that's going to get plugged into dt dt. tongue twisters, dt dp at constant h. And then even further up above, remember, dt dp at constant h was in another equation, right? So that was up here. All right, so pause the video, see if you can plug everything in to see what the final expression is going to be. So remember, we wanted, the very first equation we wrote was dt is equal to dt dp at constant h dp. And then through all these hoops that we were jumping through, we calculated what dt dp at constant h is. So plugging it all in, we've got dt is equal to minus v bar minus t dv dt at constant p over cp times dp. All right, so to find what the change in temperature is, we can integrate. So we're going to integrate this one from T1 to T2, integrate this one from P1 to P2. And now here's where we need our model. This is where our equation of state comes in. Remember at the very beginning, there was a partial derivative that you said you may be tempted to use an equation of state there, but you can't because of the variables. Well here, this should be a V underbar as well. Here I have the partial of V with respect to T at constant P. So because I've got the three variables, V, T, and P, I can use the ideal gas law in that case. So I can say that V is equal to RT over P. And I can say that the partial of V with respect to T at constant P is just RP. All right, so you take the derivative of this expression with respect to T, assuming that P is constant. All right, so I'm going to plug R over P into that expression. And when I do that, I've got back again RT over P. I'm going to plug the ideal gas law into V underbar. So minus integral of RT over P minus RT over P over CP. This whole thing is equal to 0, which makes this whole term go away. dP from P1 to P2 is equal to T1 minus T2. Okay, so the integral of 0 is the variable. No, I'm sorry. If the integral inside is 0, then the whole integral is 0. So I've got T2 minus T1 is equal to 0, or T1 is equal to T2 for an ideal gas, which makes sense. This is exactly what we had found when we did Unisim. Remember the Unisim simulation where I said ideal gas, what's the change in temperature going to be? For an ideal gas, enthalpy is only a function of temperature, and that's why we had no change in what the temperature is. So again, this is how, the idea here is we use an equation of state in an equation that we derive to find what the change in temperature is. So this is just a quick introduction. If you didn't understand quite all of this, don't worry. Again, we're going to get into this more next week. Sorry for the long video. I'm going to wrap up and conclude here.